Welcome to G Fun Facts Online. Imagine a volcano erupting. You're probably picturing a mountain of fire spewing ash and lava into the open air. But what if that eruption happened under 2 kilometers of solid ice? Beneath the immense, frozen expanses of our planet's poles lies a world of fiery turmoil. Hidden from view, a potent geological force is at play: subglacial volcanoes. This is the story of fire under ice, a dramatic intersection where the intense heat of magma meets the crushing cold of ancient glaciers. It's a phenomenon that creates bizarre landscapes, triggers some of the most powerful floods on the planet, and, astonishingly, might just hold the key to finding life on other worlds. So what exactly is a subglacial volcano? The name is pretty descriptive. It's a volcano that forms and erupts beneath a glacier or ice sheet. The presence of all that ice completely changes the game. When magma rises, it doesn't just flow out. First, its intense heat has to melt the ice above it, often carving out a vast cavern and filling it with a meltwater lake, all while still trapped under the glacier. The lava that erupts into this hidden lake cools incredibly fast. This rapid quenching doesn't create the ropey or blocky lava flows we see on land. Instead, it forms distinctive, bulbous masses of rock called pillow lavas, very similar to what you'd find at deep-sea volcanic vents. As the eruption continues, these pillows can break off and tumble down the volcano's slopes, creating layers of glassy, fragmented rock called hyaloclastite. The final shape of the volcano depends on how powerful the eruption is and how thick the ice is. If the eruption isn't strong enough to break through the ice, it forms a conical pile of these pillow lavas, known as a subglacial mound. But if the eruption is sustained and powerful enough to melt its way all the way through the ice sheet, something spectacular happens. The volcano emerges from the ice, and its lava, now erupting into the meltwater lake at the surface, spreads out horizontally. This creates a volcano with a distinctively flat top and steep sides. These formations are called tuyas. The name comes from Tuya Butte in British Columbia, Canada, and they are geological marvels. Scientists can study ancient tuyas today and use them as paleo ice indicators. The height of a tuya's flat top tells us exactly how high the surface of the ancient ice sheet was, giving us crucial data for understanding past climates. So where do we find these incredible features? You need 2 ingredients: volcanic activity and ice. The 2 best places on Earth for this are Iceland and Antarctica. Iceland sits on the mid-Atlantic ridge, a hotspot of volcanism, and is also covered in extensive glaciers. It's a natural laboratory for studying fire and ice. The island nation is home to some of the most powerful and hazardous subglacial volcanoes on Earth. Take Katla, for example. Hidden beneath the Mýrdalsjökull ice cap, Katla is one of Iceland's largest and most active volcanoes. It has erupted at least 20 times since the year 920. Roughly every 40 to 80 years. The last major eruption was in 1918, and it produced a glacial outburst flood so massive, its peak flow was estimated at 300,000 cubic meters per second. That's more than the Amazon River. Another giant is Grímsvötn, located under the vast Vatnajökull ice cap. It's Iceland's most active volcano. In 1996, an eruption melted 3 cubic kilometers of ice, leading to a colossal flood that swamped over 750 square kilometers of land. And of course, there is Eyjafjallajökull. While relatively small, its 2010 eruption became world famous. The explosive interaction of magma and meltwater created a plume of incredibly fine ash that was shot high into the atmosphere, causing massive disruption to air travel across Europe for over a week. It was a stark reminder of the global reach of these seemingly remote eruptions. Now, let's travel to the other pole, Antarctica. This icy continent hides the largest glacial-volcanic province on the planet. But we didn't know the full extent of it until recently. In 2017, a groundbreaking study revealed an astonishing 138 volcanoes beneath the West Antarctic ice sheet, 91 of which were completely unknown. This discovery identified the West Antarctic Rift System as the densest volcanic region on Earth, with volcanoes ranging from 100 meters to nearly 4,000 meters tall. This raised immediate concerns. What would happen if one or more of these volcanoes erupted? The heat could rapidly melt the ice sheet from below, creating a feedback loop of accelerated ice flow towards the sea. We already have evidence this is happening. A newly discovered heat source, believed to be volcanic, is thought to be contributing to the rapid melting of the critical Pine Island Glacier. And we know these volcanoes can be powerful. A major eruption in this region 200 years ago, the largest in Antarctica in the last 10,000 years, blew a hole in the ice sheet and sent ash 12 kilometers into the sky. Peering through kilometers of solid ice to study an active volcano sounds like science fiction. But geologists have developed an incredible toolkit to do just that. One of the primary methods is ice-penetrating radar. By flying aircraft with radar instruments over the ice sheets, scientists can map the bedrock topography below, measure the ice thickness, and identify the telltale shapes of volcanoes and subglacial lakes. This radar data was instrumental in that 2017 discovery of all those new volcanoes in Antarctica. Next is seismic monitoring. Just like any other volcano, subglacial ones generate earthquakes as magma moves around beneath them. Networks of seismometers placed on the ice can detect these tremors. During the 2014 Bárðarbunga eruption in Iceland, scientists tracked a magma-filled dike migrating 48 kilometers beneath the Vatnajökull ice cap by recording over 30,000 earthquakes. Another powerful tool is GPS. As a magma chamber fills, it can cause the ground surface to bulge upwards. By placing high-precision GPS stations on a glacier's surface, scientists can measure these subtle movements with millimeter-level accuracy, giving them a clear warning sign that a volcano is inflating and might be preparing to erupt. Finally, they analyze the water. Scientists test the chemical composition of meltwater from glacial rivers to detect volcanic gases like carbon dioxide and sulfur dioxide. These dissolved chemicals are a clear fingerprint of magmatic activity happening deep beneath the ice. The combination of intense heat and immense ice can unleash some truly terrifying hazards. The most significant and frequent is the jökulhlaup. That's an Icelandic term that means glacial run, but a better translation might be catastrophic glacial outburst flood. These happen when the meltwater from an eruption trapped in a subglacial lake is suddenly released. The overlying ice acts as a dam, but as the water pressure builds, it can literally lift the entire glacier, creating an escape route. The release is incredibly rapid. The 1996 jökulhlaup from Grímsvötn in Iceland had a peak discharge of 50,000 cubic meters per second. These floods are not just water, they are a slurry of water, massive chunks of ice, and huge amounts of rock and sediment. They can destroy everything in their path, including bridges, roads, and entire landscapes. Another major hazard is lahars, which are fast-moving mud flows. When the meltwater mixes with loose volcanic ash and rock, it can form a dense, concrete-like flow that travels at high speed down the volcano's slopes, burying everything. And then there's the ash. As we saw with Eyjafjallajökull, the explosive interaction of magma and water is very efficient at creating fine-grained ash. This ash poses a serious threat to aviation. It's abrasive, but more critically, the silicate particles can melt in the heat of a jet engine and then re-solidify on the cooler turbine blades, causing the engine to fail. This is why a single eruption in Iceland can shut down airspace across an entire continent, causing billions of dollars in economic disruption. But amidst all this violent turmoil, in the cold, dark, high-pressure world beneath the ice, something incredible is happening. The geothermal heat from these volcanoes creates unexpected oases for life. These unique ecosystems, powered by chemicals instead of sunlight, might hold clues to how life first evolved on Earth and where we might find it elsewhere in the solar system. The process that makes this possible is called chemosynthesis. Instead of photosynthesis, specialized microorganisms called extremophiles derive their energy from chemical reactions. They eat inorganic compounds like hydrogen sulfide, iron, and methane that are released from volcanic vents. This allows them to create organic matter, forming the base of a food web in total darkness. Researchers have found tantalizing evidence of these hidden ecosystems around the world. In steam-carved ice caves near Mount Erebus, an active volcano in Antarctica, temperatures can be as high as 25 degrees Celsius. Scientists have found DNA from a variety of organisms, some of which they couldn't identify, hinting at unknown species living in these sheltered, warm pockets. Studies of subglacial lakes in Iceland have also found diverse microbial communities, supported by the heat and chemical nutrients from volcanoes like Grímsvötn. Using clean drilling technology to avoid contamination, missions to subglacial lakes in Antarctica have provided definitive proof of viable microbial ecosystems, with diverse communities of microbes that literally mine the rocks for energy. This has profound implications for astrobiology, the search for extraterrestrial life. Icy moons like Jupiter's Europa and Saturn's Enceladus are thought to have vast liquid water oceans beneath their frozen shells. If there's volcanic activity on the seafloor of those moons, it could create conditions very similar to what we see under our own planet's ice sheets, potentially supporting chemosynthetic life. Earth's hidden volcanoes are our best model for what life might look like in these alien oceans. Finally, the story of fire and ice is intertwined with our changing climate, creating a complex and potentially dangerous feedback loop. During past ice ages, the immense weight of ice sheets pushed down on the Earth's crust. As the climate warmed and the ice melted, that weight was removed and the crust began to slowly rebound upwards. This reduction in pressure on the magma chambers below can make eruptions more likely. Studies have shown that periods of rapid deglaciation in places like Iceland were followed by periods of increased volcanic activity. This leads to a worrying question for our future. As our planet continues to warm and our remaining glaciers and ice sheets melt at an accelerating rate, could we see an increase in volcanic eruptions? The discovery of that huge volcanic field under the West Antarctic ice sheet is a particular concern. The thinning of the ice there could trigger more eruptions, which would, in turn, add more heat to the base of the ice, accelerating melting even further. This is a classic positive feedback loop. Melting causes eruptions, which cause more melting. The long-term implications for global sea levels are a serious concern for scientists. The world of subglacial volcanoes is a realm of stark contrasts. It's where the primordial heat of Earth's core clashes with the frigid power of its frozen surface. These hidden volcanoes are a testament to the dynamic and often violent nature of our planet. Yet, in this turmoil, there is the unexpected whisper of life, with chemosynthetic ecosystems that rewrite our understanding of biology and give us hope in the search for life beyond Earth. As our planet's ice continues to recede, studying these fiery giants takes on a new urgency. Understanding the delicate balance between fire and ice is crucial for predicting hazards, for understanding our planet's past, and for grasping the complex feedback loops that will shape our future in a warming world. It's a powerful reminder that there are still vast, unexplored frontiers right here on our own planet, holding secrets we are only just beginning to reveal.